We have a good few minutes here of our time to spare for this quick video here. Thank you everyone for watching this video and joining me. I am Mr. Ish. We're looking here at an easy alternative derivation of this natural log derivative, an alternative route. Not the limit approach, but an alternative. You can call it like an inverse function style of approach. We know very easily a derivative of the natural log ax always gives you 1 over x with this a disappearing. We want to just present a good approach with regards to this specific derivative. We know this right here is a function that's being applied in terms of its derivative. If you have a function which looks very well like this, f of x is equal to a natural log ax, you know you can write that as y is equal to a natural log ax. If you were to solve for that ax component for right now and take the natural log on the other side, which very well brings the inverse functional properties between the natural log and the exponential, you know you'll get e to the y. Ax is equal to e to the y, and we can like save this little expression here on the side, and now we can very easily just solve for the x. We'll have e to the y over a is equal to x. From this component over here, if you were hypothetically just to do implicit differentiation, implicitly derive a derivative utilizing this, you'll be looking at derivative of this x component or the variable, and you can push out this little 1 over a coefficient here on the side while you do the derivative of this y variable with respect to that y. What you're going to get, and what will you solve for? You'll solve for this dy over dx, because we know all along dy over dx is always equal to y prime, which is the derivative of your expression with respect to y. Derivative of x is just a 1, and 1 over a stays out over here. Derivative of e to the y is just e to the y, and we have dy over dx. This little route requires the assumption that anytime you have something like derivative of e to the x, it's always e to the x, and we know we could very well satisfy that assumption. If you have a exponential function and you look at tangent values at these specified domain points or these x-axis points, and you plot x-axis values to the slopes of your tangent lines, you very well draw a derivative of your original function, which was f of x, and it very well mirrors your original function, which is now e to the x. The derivative of e to the x by means of the graphic derivation procedure yields a derivative which is still e to the x. So we know we can very well utilize that assumption right over here. You solve for dy over dx, you take a on the other side and e to the y on the other side. You have dy over dx is equal to a over e to the y. Of course, a cross multiplies upwards and e to the y cross multiplies downwards, and you have dy over dx is equal to a over e to the power of y. And then we look right over here, we know that e to the power of y is also equal to a to the x. We can do that substitution, you can call it back substitution. A divided by ax, these cancel out and you get your derivative right over here, 1 over x, because when these cancel out you'll be left with 1 over x. And then this procedure, you can call this like an easy alternative route. This procedure is right done over here, 1 over x, the a value disappeared, and the derivative of anything which looked like this is exactly that. It's not just a new or unique procedure, it's a mix of a variety of functional properties, the inverse properties of logs and natural logs, all of that, and it's an easy derivation route for this natural log derivative. If you want to keep this in mind versus the more technical limit approach, there's nothing wrong with you doing that. Thank you for watching. Have a nice day.